Welcome to Talk Tensors.
Hey, everyone.
So for this deep dive, I want you to picture the year 2017.
Oh, wow. Going back a bit.
Yeah, we're doing a bit of time travel today.
Yeah.
Because if you look around the world of machine learning at that exact moment in history, you are going to see a field that is just absolutely unequivocally obsessed with one single thing.
Depth. It was all about depth.
Exactly. Depth. Everyone is pushing convolutional neural networks, or CNNs as we usually call them, to their absolute breaking points just by stacking more and more layers.
Right. We're talking about the era of VGG-nets, the inception models, and of course, the mighty ResNet.
Heavy hitters. And the entire philosophy of the time seems to be this like brute force approach. If your model isn't working, if it isn't classifying images accurately enough for you, well, the answer is just to make it deeper.
Yeah, just throw more layers at it, more compute, more layers.
Right. And the focus is almost entirely on spatial features, capturing the perfect edges, the perfect textures, the spatial correlations across an entire image.
Which makes sense intuitively, but it was creating a massive blind spot.
It totally was. And that is why today we are doing a deep dive into a seminal paper that actually won the ImageNet 2017 classification competition by doing something radically different.
It won by looking sideways, essentially.
Exactly. Instead of obsessing over spatial data, this paper focused on the relationships between the channels themselves.
And it is really difficult to overstate just how much of a paradigm shift this was for computer vision.
It really shook things up. So what are we actually calling this architecture?
The paper we are unpacking today introduces what the authors call Squeeze-and-Excitation Networks, or, SENets for short.
SENets, okay.
Yeah.
And what's the core thesis here?
To distill their entire thesis down to a single mechanism, it's basically this. By explicitly modeling the interdependencies between channels, a neural network can selectively emphasize informative features.
And I assume it suppresses the less useful ones at the same time.
Exactly. It suppresses the noise. But here is the kicker. It achieves this dynamic recalibration with almost zero extra computational cost.
Okay, see, I want to really dig into that zero extra cost claim later, because honestly, anytime someone tells me I can get state-of-the-art performance for free, my skeptical alarms start ringing really loudly.
Well, it's a very healthy reaction in this field, honestly.
Right. But before we get to the actual squeeze and excitation mechanisms, the actual math, let's set the stage a bit more. Let's talk about the climate of 2017.
The pre-Senet landscape.
Yeah. What were the invisible walls that researchers were hitting right before this paper dropped? Because, obviously the obsession with depth wasn't happening in a vacuum. There was a reason everyone was building these massive towering neural networks.
Well, to understand the mindset of the field at that time, we really have to look at the evolution of the convolution operator itself.
The basic building block.
Exactly. The convolution operator is the absolute central engine of CNNs. It is what drives visual recognition. And historically, a broad range of prior research had relentlessly investigated the spatial component of this operator.
Meaning they were obsessed with the literal layout of the pixels.
Right. Researchers were trying to strengthen the representational power of a CNN by enhancing the quality of spatial encodings. They wanted the network to be better at finding shapes,
Like recognizing how a curve connects to a straight line.
Yeah, or how a specific cluster of pixels forms a rough texture.
Which makes total sense, because if you can't see the curve of a wheel or the hard edge of a road, you definitely can't build a self-driving car. So the instinct was just to, give the network more opportunities to find those shapes.
That was the driving logic. So you had VG-nets, which came out of Oxford a few years prior to this paper, and they proved that sheer depth could significantly increase representation quality.
How did they do that? Just massive layers.
Yeah. Basically, yeah. They just stacked a massive number of very small 3x3 convolutional filters directly on top of each other.
Just a giant tower of 3x3 grids.
Right. And then you had inception models, which were pioneered by Google. They took a slightly different approach. They incorporated multi-scale processes.
Multi-scale meaning they didn't just use 3x3 filters.
Exactly. Instead of just stacking sequentially, an inception block looks at the image with different size filters all at once. Say a 1x1, a 3x3, and a 5x5, all simultaneously.
Oh, and then it just smashes the results together.
It concatenates them. Yeah. It was an attempt to capture spatial structures at varying scales of detail in a single pass.
But the problem with both of those approaches is that eventually your signal just dies, right?
The vanishing gradient problem?
Yeah, the vanishing gradient. I always visualize it like a massive game of telephone.
That's actually a great way to look at it.
Right, because the prediction at the very end of the network has to send an error signal all the way back to the first layer to update the weights. But if that signal has to pass through, say, 200 layers of multiplication, and the numbers are all small fractions, the signal just gets infinitely smaller.
Until it vanishes into literally nothing.
And the first layer never learns anything. It just stays random.
The telephone game is a perfect analogy. As you chain those derivatives together using the calculus chain rule backward through the network, the gradients shrink exponentially.
Which is a huge wall to hit.
It was. And that specific roadblock is what led to the development of ResNets, or residual networks.
Ah, the famous skip connections.
Exactly. ResNets introduced identity-based skip connections. Instead of forcing the signal to travel through every single layer sequentially, a skip connection acts like a bypass valve.
It routes around the traffic.
It takes the original input to a block of layers and adds it directly to the output of that block. This creates a clean, uninterrupted gradient highway backward through the entire network,
allowing models to scale to hundreds of layers without the signal vanishing. Okay, so I think I have the 2017 picture now.
It was a very tall picture.
Yeah, very tall. We have the VGG approach of deep stacking, the inception approach of multi-scale branching, and the ResNet bypass valves to keep the gradients alive. Everyone is essentially building these incredibly complex skyscrapers to capture spatial structure.
They were, and at the same time, we were just beginning to see a shift toward algorithmic architecture search.
You mean AI designing AI?
Yeah, concepts like neuroevolution and reinforcement learning were starting to be used to automatically learn network topologies, taking the human out of the loop, essentially.
But manual, human-crafted design was still the norm, right?
It was still very much the gold standard, and the human designers had a collective blind spot.
The blind spot that this paper exposes.
Exactly. Much of the research concentrated on reducing model and computational complexity based on a very specific, totally unquestioned assumption.
And what was that assumption?
That channel relationships could simply be formulated as a byproduct of local receptive fields.
Okay, hold up. Let's pause and define our terms here, because I feel like this is where the paper's core insight lives.
It absolutely is.
When we say channel, what exactly are we talking about in the context of a CNN? Because a casual listener might just think of the red, green, and blue color channels of a digital photo.
Right, and it is a vital distinction to make. You are correct that an input image starts with 3 channels: red, green, and blue. But as that image passes through the very first convolutional layer, it is transformed into a feature map.
Okay, a feature map. What are the dimensions of that?
It has a spatial height, a spatial width, and a depth. And that depth is what we call channels.
So it's not colors anymore.
No, not at all. In the deeper layers of a network, you might have 256, 512, or even 2048 channels. And each one of those channels represents a specific feature detector.
Oh, okay. So give me an example of what a channel actually detects.
Well, for example, channel number 5 might be highly active when it sees a vertical edge anywhere in the image. Channel number 50 might light up when it detects the texture of dog fur.
And channel 100 might track the presence of a circular shape, like an eye or a tire.
Exactly.
So imagine a stack of transparent tracing paper over an image.
Oh, I like that visual.
Right. So the first sheet of tracing paper is only drawing the vertical lines. The second sheet is only drawing the horizontal lines. The 50th sheet is highlighting everywhere there is fur. Each sheet is a channel.
That is a highly accurate mental model.
And the network has to somehow combine all these transparent sheets to eventually realize, oh, hey, I am looking at a dog sitting on a couch.
Right. Now let's look at the local receptive field, part of the assumption that the field was making. The standard convolution operator does something very specific. It fuses spatial and channel-wise information together.
But it does it locally, right?
Strictly locally. A convolutional filter is typically a small grid, often 3 pixels by 3 pixels. It slides across the feature map, looking at a tiny 3 by 3 window of spatial data.
But it's looking deep, right? Through all the transparent sheets.
Yes. It looks through all the channels at that specific location simultaneously. It computes a weighted sum across all channels within that tiny local window to produce a single value in the next layer.
And here's the inherent problem with that. This is the exact unsolved problem this paper tackles. Because of that sliding window, the convolution is mathematically blind to the big picture.
It can't see the forest for the trees.
Right. Let me try another analogy. Imagine you are trying to understand a massive, intricate mural painted on a wall, but you are forced to look at it through an empty paper towel tube.
A paper towel tube. Okay, I'm with you.
You can see the local details perfectly within your tiny field of view. You can see the sharp edge of a painted leaf or the specific shade of blue in a painted sky. But you completely miss the global context.
Because you can't see what's outside the tube.
Exactly. You have no idea how the blue sky relates to the ocean painted on the completely opposite side of the mural. So in the context of our neural network, how on earth can feature channel number 5, which found a floppy dog ear in the top left corner, know what feature channel number 50 is doing when it finds a curly dog tail in the bottom right corner?
It can't. It literally can't. That is the fundamental limitation.
They are completely isolated from each other spatially.
Right. Because the output of a standard convolution is produced by a summation across all the input channels within that paper towel tube, the channel dependencies are implicitly embedded in the output.
But they're tangled up.
Heavily entangled with the local spatial correlation. The channel relationships modeled by a standard convolution are inherently implicit, they are entangled, and they are incredibly local.
I suppose the obvious question a listener might have is, well, why not just use a bigger paper towel tube?
Just look at the whole image at once.
Yeah, why not just make the convolutional filter the exact same size as the entire image? Say 224 pixels by 224 pixels. Then it would see everything at once. No more blind spots.
The math makes that practically impossible due to the sheer number of parameters.
Because it multiplies out of control.
It explodes. Let's do the math. A single 3x3 filter looking across 256 channels requires about 2,300 parameters.
Okay, 2,300. That's tiny.
Very tiny. Now, a 224 by 224 filter looking across those same 256 channels, that would require almost 13 million parameters.
Oh, wow. And that is just for one single filter.
In one single layer, your network would explode into billions or trillions of parameters instantly.
It means it would require impossible amounts of memory and compute.
And it would immediately overfit to the training data. It would just memorize the training set instead of learning patterns. The beauty of the small sliding window is that it shares weights across the image, keeping the parameter count low.
Okay, so you are trapped. You need the small window to keep the math manageable, but the small window makes you blind to the global context.
It's a massive paradox.
If channel 5 has found a dog ear and channel 50 has found a curly tail, they don't really know how to talk to each other to confirm, hey, we're looking at a pug, until much, much deeper in the network.
Right, after many layers of convolutions have slowly, incrementally expanded that effective field of view.
Which takes forever and wastes compute. So that is the exact tension the authors identified. And it leads to their breakthrough idea.
The hypothesis was simple, but profound. They hypothesized that the learning of convolutional features could be massively enhanced if we explicitly model the interdependencies between the channels.
But without blowing up the parameter count like we just talked about.
Exactly. They wanted to decouple the channel relationships from the local spatial filters. They wanted to give the network access to global information so it could dynamically recalibrate the feature maps on the fly.
Which brings us to the actual architecture they invented to solve this, the squeeze-and-excitation block. The SE block.
The star of the show.
This is their solution to the paper towel tube problem. So how do we actually give a local filter a global perspective without requiring a supercomputer to process all that extra information?
The genius of the SE block lies in how it accomplishes this global perspective through a highly efficient two-step process.
Step 1 and step 2. Let's hear them.
Step 1 is the squeeze. And step 2 is the excitation. Let's walk through the math of the squeeze first, which the authors formally call global information embedding.
Okay, I'm imagining I have just run a standard convolution. I have an output feature map. Let's call it $2.
Okay, $2. And this feature map has 3 dimensions: height, width, and channels. So H by W by C.
Right. So let's say we are somewhere in the middle of ResNet. Our feature map might have a spatial resolution of 56 by 56 pixels and a depth of 256 channels.
Exactly. But again, each unit of that transformation is stuck in its local receptive field. To mitigate this, the authors propose squeezing the global spatial information into a single channel descriptor.
Squeezing it how?
They do this using an operation called global average pooling. Mathematically, they take the spatial dimensions, that 56 by 56 grid for a single channel, and they literally just average all of those values together.
Wait, they just add them all up and divide by the total?
Yes. They shrink the entire spatial grid of a single channel down to one single number.
Wow. So if channel 50 is our transparent sheet tracking floppy earness, the squeeze operation just averages all 3,136 of those spatial values into one single scalar value.
That's the math.
That one number now represents the global floppy earness of that entire channel, completely stripped of any specific location data. It doesn't care where the floppy ear is, it just cares how much floppy ear exists in the image overall.
You're tracking the exact logic the authors use. And when you perform that averaging operation for every single one of the 256 channels, your massive 56 by 56 by 256 feature map gets smashed down.
Smashed down to what?
Down to a tiny 1 by 1 by 256 vector.
Oh, that's tiny.
This result is the channel descriptor. It is an embedding of the global distribution of the channel-wise feature responses. Now, the authors actually ran ablation studies on this specific step.
What did they test it against?
They tested using global max pooling instead of global average pooling.
Okay, my intuition says max pooling would be better.
Really? Why?
Because if I'm looking for a floppy ear and I find a massive undeniable activation for a floppy ear in the top left corner, I want to preserve that strong signal. If I average it out with all the background pixels that have zero floppy earness, doesn't that just dilute the signal? Why would you want the average instead of the maximum?
It's a fair question, but the data actually points the other way. They found that while both are definitely effective, average pooling performs slightly better.
By how much?
Specifically in their SE-ResNet 50 tests on ImageNet, average pooling achieved a 6.03% top 5 error, whereas max pooling resulted in a 6.09% top 5 error.
So a small difference, but a consistent one.
Right. And if we connect this to what the network is actually trying to understand, it makes sense. Think of it like taking an economic survey of a city.
Okay, I like economic surveys.
Max pooling is like finding the single richest billionaire in the city and using their wealth to represent the entire population.
Which is wildly misleading.
Exactly. It gives you the loudest signal, the peak intensity. But average pooling acts as a census. It is a better statistic for the overall global distribution of the feature responses. It tells you about the true prevalence of the feature across the entire image.
Ah, okay. That actually clicks perfectly for me. If a texture channel is tracking dog fur, the fur is going to be spread out across hundreds of pixels.
Yeah.
Max pooling would just grab the one shiniest pixel of fur,
Yeah.
while average pooling captures the massive total volume of fur present in the image.
Which is a much more stable metric for the overall context.
Okay, so we've squeezed the spatial information, we've stripped away the where and kept the how much. We now have a 1 by 1 by C vector that summarizes the global state of every channel.
Right.
What do we do with it? That brings us to step 2.
Step 2 is the excitation step, or what the authors call adaptive recalibration.
This is where the magic happens.
This is where the actual intelligence of the SE block resides. The excitation step takes that squeezed descriptor and uses it to create a set of weights for the channels.
So it's generating multipliers.
It is essentially a self-gating mechanism. And to do this effectively, the function needs to meet 2 strict criteria. First, it must be flexible enough to learn a complex, nonlinear interaction between the channels.
Right, it can't just be a simple straight line equation.
Exactly.
Oh.
And second, it must learn a non-mutually exclusive relationship. We want the network to be able to emphasize multiple different channels simultaneously.
So we don't want a situation where if the fur channel is turned on, the dog tag channel is forced to turn off.
Right. They need to be able to fire together. And to achieve this, they use a bottleneck architecture.
A bottleneck, which is a very specific arrangement of neural network layers.
Yes, it consists of 2 fully connected layers with a real U activation function sandwiched in between them and a sigmoid activation function at the very end.
Let's trace the data as it flows through that bottleneck.
Yeah.
Because I want to visualize it.
Sure. You start with your vector of size C. Let's say it's 256. The first fully connected layer reduces the dimensionality by a ratio called R.
What's R usually set to?
Usually 16. So the data is compressed from a size of 256 down to 256 divided by 16.
Which is 16.
Right. Your vector shrinks to just 16 numbers. Then it hits the real U nonlinearity, which turns any negative numbers to 0.
A standard real U step.
Then the second fully connected layer expands the dimensionality back up from 16 to the original size of 256. Finally, it passes through the sigmoid function.
Okay, I have to stop you here.
What's wrong?
This is where my skeptical alarms from earlier are going off. We were talking about adding fully connected layers. Historically, fully connected layers, also known as dense layers, are the most parameter-heavy, memory-hogging parts of a neural network.
They absolutely can be.
And you were telling me they do this little shrink and expand dance at every single block in a 50-layer network. Why not just have one fully connected layer that maps 256 directly to 256? Why go through the headache of the bottleneck at all?
It is a critical design choice, and it directly answers your skepticism about computational cost. There are three main reasons for the bottleneck, and the first is exactly what you are concerned about: limiting model complexity.
Because mapping directly is too expensive.
Exactly. If you map a 256-dimensional vector directly to a 256-dimensional vector using a single dense layer, the number of parameters scales with the square of the channel.
So 256 times 256.
Which is over 65,000 parameters for one block.
Yeah, that would add up fast.
By introducing the reduction ratio of 16, the first layer is 256 times 16, and the second layer is 16 times 256. You have reduced the parameter count from over 65,000 down to roughly 8,000.
Okay. That is a massive computational saving.
It shrinks the overhead dramatically.
Okay, so the bottleneck forces the math to stay manageable. What are the other two reasons?
The second reason is that the bottleneck allows you to introduce the ReLU activation function in the middle. This adds a necessary nonlinearity, which drastically increases the representational power of the gating mechanism.
Because a single linear layer couldn't capture those complex, nuanced relationships between the channels.
Exactly. And the third reason is that it acts as a regularizer.
A regularizer?
How? By forcing the data through a narrow 16-dimensional bottleneck, you are forcing the network to compress the information. It compels the network to learn only the most essential, robust interchannel correlations.
Rather than just memorizing noisy, spurious connections.
Right. It aids in generalization.
I think I have an analogy for this. It's like a corporate hierarchy.
Let's hear it.
Instead of 256 frontline workers all trying to shout at each other and coordinate a project, they all send a quick summary to a tiny team of 16 managers. Those 16 managers find the overall patterns, decide on a strategy, and then broadcast that strategy back out to the 256 workers.
That is an excellent analogy. It's way more efficient, and it forces them to focus only on the big picture.
Love it. Okay, now let's look at the final piece of the excitation step, the sigmoid activation function.
This is what guarantees those non-mutually exclusive relationships we talked about earlier.
Let me guess. If they had used a softmax function instead, which is standard for classification, it would turn the output into a probability distribution.
It would. A softmax forces all the outputs to sum to exactly 1.0.
So it's like slicing up a single pie. If the floppy ear channel gets 90% of the pie, the curly tail channel can only get 10%. They are forced to compete for relevance.
That is the exact mathematical trap of softmax. But a sigmoid evaluates each channel entirely independently. It squashes the output of each channel to a scalar value between 0 and 1.
So multiple channels can be fully excited, receiving a value of like 0.99 at the exact same time.
They aren't competing for a single pool of relevance. And the authors actually proved this necessity with another ablation study.
Oh, they tested it?
Yeah. When they replaced the sigmoid with a softmax or a ton function, performance degraded. And when they replaced it with a ReLU,
let me guess, it broke.
It completely broke the network. The performance dropped below the baseline model that didn't even have SE blocks to begin with.
Wow.
The bounding to a range between 0 and 1 is mathematically required for the final step to work.
Which leads us to step 3, the scale. This is the easiest part of the whole paper.
It really is.
We now have a set of C-scalar weights, one for each channel, all sitting somewhere between 0 and 1. You simply take these scalar weights and multiply them channel-wise with the original spatial feature map, our U matrix.
It is brilliant in its simplicity.
You are literally just turning the volume knobs up or down on each individual channel based on the global context.
Right.
So if the tiny team of managers looks at the global summary and says, based on the overall distribution of textures, we are definitely looking at a dog, they send a signal close to 1.0 to the floppy ear channel,
which preserves its spatial map entirely.
But if the managers realize, hey, we are looking at a dog, so this channel tracking metallic car reflections is utterly useless right now, they send a weight of 0.01 to the metal reflection channel,
effectively muting it.
It is dynamic, input-conditioned recalibration.
And it functions as a highly efficient form of self-attention on the channels. Unlike standard attention mechanisms like those found in transformers, which often require heavy, complex matrix multiplications across massive spatial dimensions, this channel-wise attention is computationally microscopic.
Which perfectly sets up the engineering marvel of this paper. Because, a great mathematical theory is wonderful, but if implementing it requires you to completely redesign your network from scratch, no one is going to use it.
Sure.
Or if it requires $1 million supercomputer cluster just to train the thing, No one in the real world is going to adopt it. So let's look at the actual complexity and integration of these SE blocks. How hard is it to actually use this in practice?
The integration strategy is arguably the strongest selling point for practitioners. SE blocks are entirely generic. They are designed to be true drop-in replacements.
Meaning I don't have to rewrite my whole code base.
Exactly. You can take an existing state-of-the-art architecture like a VGGNet, an inception network, a ResNet or a ResNext, and simply insert SE blocks into the existing code with just a few lines of Python.
For a standard architecture like VGGNet, which is just a straight line of layers, you literally just insert an SE block after the nonlinearity following each convolution.
Simple as that.
But for a ResNet, it gets a bit trickier, right? Because ResNets have that bypass valve, the identity skip connection.
Yeah, that complicates the wiring slightly.
So they actually had to run an ablation study to figure out exactly where inside the residual module the SE block should go.
It did. Inside a residual block, the signal branches off, goes through a couple of convolutions, and then sums back up with the main identity branch. They tested a few variants.
Let's go through them.
The SEPRE block placed the squeeze and excitation recalibration before the residual unit's convolutions even started. The SE identity block placed it on the identity connection itself, parallel to the residual unit.
Okay, and what else?
And the SE post block placed it after the summation, modifying the merged signal. Finally, the standard SE block placement was inside the residual branch right before it summed back with the identity branch.
Okay, let me theorize on this for a second.
Go for it.
If the whole point of a ResNet skip connection is to create a clean, unadulterated gradient highway for the backward pass, I would imagine the SE post placement is a terrible idea.
Why do you say that?
Because if you place a dynamic nonlinear scaling operation after the summation, you are effectively putting a toll booth on the gradient highway. You are corrupting the clean signal that the skip connection was specifically designed to protect.
Your intuition is spot on. The empirical results showed exactly that.
Yes, validated.
The standard placement inside the residual branch prior to aggregation and the SEPRE placement performed similarly well. The SE identity was also viable, but the S-host block led to a noticeable drop in performance.
Because of the toll booth.
Right. Applying a dynamic, nonlinear scaling to the main identity pathway disrupts the optimization benefits of residual networks. As long as you apply the SE block to the residual branch prior to aggregation, it integrates beautifully.
Okay, so it drops in easily. But let's return to your claim of almost zero cost.
The GFLOP.
Yes, let's talk GFLOPs. Giga floating point operations per second. This is the currency of deep learning compute. How much does this actually cost to run?
Let's use ResNet 50 as our baseline standard. A standard ResNet 50 requires roughly 3.86 GFLOPs and a single forward pass for a standard 224 by 224 pixel input image.
Okay, 3.86.
When you upgrade that exact same architecture to an SE ResNet 50 using that reduction ratio of 16 in the bottlenecks, the compute requirement goes up to roughly 3.87 GFLOPs.
Wait, let me make sure I am hearing those numbers right. 3.86 jumps to 3.87. That is a 0.26% relative increase in computational burden. That is a rounding error. How is that physically possible when you are adding 2 new dense layers to every single block?
It comes back to the dimensional math we discussed. The global average pooling operation is computationally trivial. Averaging numbers is virtually free for a GPU.
True.
And the 2 fully connected layers in the bottleneck are operating on tiny vectors. They are compressing 256 numbers to 16 and expanding 16 back to 256.
Compared to the huge spatial grids.
Exactly. Compare that to a spatial convolution that requires multiplying 3 by 3 grids across hundreds of channels for tens of thousands of spatial locations. The bottleneck math is a drop in the ocean compared to the spatial convolutions. And the final scaling is just a simple element-wise multiplication.
It is like adding a tiny carbon fiber aerodynamic spoiler to a heavy sports car. It improves your downforce and top speed by 10%, but it only adds a few ounces of weight to a 2-ton vehicle. It's almost free performance.
And the comparison the authors make to ResNet 101 is where this efficiency gets truly absurd.
Lay it on me.
Yes, the depth comparison is where the paradigm shift really crystallizes. An SE ResNet 50 achieves a top 5 error rate of 6.62% on ImageNet. A standard, much deeper ResNet 101 achieves a top 5 error of 6.52%.
So the 50-layer network with SE blocks is approaching the exact accuracy of the 101-layer network.
But look at the compute required. The SE ResNet 50 requires 3.87 GFLOPs. The standard ResNet 101 requires 7.58 GFLOPs.
That is mind-blowing. You are getting almost the exact same accuracy for roughly half the total computational burden.
Half the compute.
If I am deploying a model in the real world, that means I can run my inference twice as fast, or I can run it on hardware that is half as expensive just by swapping deeper spatial layers for shallow channel recalibration.
It fundamentally challenged the deeper is always better mentality that was so prevalent. However, to be fully rigorous, we must also look at parameter overhead.
Right, because compute cycles are only one constraint. Memory footprint, the sheer amount of RAM needed to hold the model weights, is just as important.
Especially for edge devices. Adding SE blocks to a ResNet 50 introduces about 2.5 million additional parameters. Since the original ResNet 50 has about 25 million parameters, that equates to roughly a 10% increase in memory footprint.
A 10% increase isn't nothing. If you are a mobile developer trying to squeeze an app onto an older smartphone, every megabyte counts.
True. But the authors provided a crucial, highly practical optimization. They analyzed where those parameters were actually coming from.
And where were they?
As you go deeper into a CNN, the spatial dimensions shrink, but the number of channels expands massively. The first layers might have 64 channels. The final layers of a ResNet 50 have 2048 channels.
Oh, right, because the fully connected layers in the SE bottleneck scale with the channel dimension, the vast majority of those 2.5 million new parameters are concentrated in the final stage of the network, operating on those 2048 channels.
Exactly.
So what is the workaround? Do you just increase the reduction ratio at the end?
Yeah.
Make it bigger?
The workaround is even simpler. They found that if you simply delete the SE blocks from that final stage entirely, you only lose a minuscule amount of accuracy.
Like how much?
Less than 0.1% on ImageNet.
Wow.
But by removing those final blocks, you reduce the parameter overhead from a 10% increase down to just a roughly 4% increase.
That is the ultimate 80-20 rule in action, or in this case, the 994 rule. You get 99% of the performance benefit for a 4% memory cost.
It's incredibly efficient.
We will actually talk about why those final SE blocks don't matter as much mathematically when we open the black box later, because the internal logic of the network at that stage is fascinating. But first, let's look at the actual empirical results.
The proof of the pudding.
Right. We have seen the elegant math. We have seen the microscopic computational cost. Did this actually work in the wild?
The benchmarks are undeniable. Let's start with the big one, the catalyst for the paper. The ImageNet Large-Scale Visual Recognition Challenge, ILS-VRC 2017.
The Olympics of computer vision.
Exactly. The ImageNet dataset is a mammoth undertaking. It contains over 1.2 million training images, meticulously categorized across 1,000 different classes. Winning this competition was the ultimate validation for any new architecture.
And they entered with this.
Squeeze-and-Excitation Networks formed the foundational core of their submission, and they won first place.
And they didn't just squeak by, right? They crushed the existing state-of-the-art.
They really did. They achieved a top 5 error rate of 2.251%. To put that in perspective, the winning entry from the previous year, 2016, had an error rate of 2.991%.
So the Senate achieved a roughly 25% relative improvement over the world's best model in a single year.
Yes.
In the world of ImageNet, where hundreds of the smartest engineers on Earth fight tooth and nail to shave off hundredths of a percent, dropping the error by almost 0.75% is a seismic event.
Their winning model was dubbed SENet 154. It was constructed by taking a modified ResNext architecture, which was already a highly advanced model that incorporated grouped convolutions, and integrating SE blocks throughout its depth.
Did they use any other tricks?
They also utilized standard competition techniques, such as applying dropout layers to prevent overfitting, using label smoothing regularization, and employing a multi-scale, multi-crop fusion strategy for the final evaluation.
But the core algorithmic engine driving that massive leap in performance was the SE block.
Undoubtedly.
But, there's always a lingering doubt with competition winners. Sometimes a mathematical trick works perfectly on ImageNet because it overfits to the specific quirks, biases, or scale of that particular data set.
That happens quite often.
Right. And then, when you try to apply that same trick to a different problem in the real world, it completely falls apart. Did the squeeze and excitation mechanism generalize beyond ImageNet?
It generalized exceptionally well across domains. The authors ran a battery of rigorous tests to prove the robustness of the mechanism. First, they looked at the other end of the resolution spectrum, CFAR 10 and CFAR 100.
Oh, the tiny images.
Yeah, these are datasets composed of tiny 32 by 32 pixel images categorized into 10 and 100 classes, respectively. They integrated SE blocks into several popular architectures for this dataset, including ResNet, Wide ResNet, and Shake networks.
And the results?
In every single configuration, the SENet counterpart outperformed the baseline. For example, on CFAR 10, adding SE blocks to a ResNet 110 dropped the error rate from 6.37% down to 5.21%.
That proves it works on low-resolution imagery, where spatial details are incredibly scarce. But what about tasks that require a totally different type of visual reasoning? Not just identifying a single centralized object, but understanding an entire scene.
For that, they tested their model on the Places 365 Challenge dataset.
Okay, what is that?
This is a massive dataset of 8 million images distributed across 365 different scene categories. Scene classification is highly complex because it requires the network to understand abstraction rather than just localizing a specific object.
Right, you aren't just looking for a dog. You are trying to determine if a room is a kitchen or a dining room.
Exactly. That requires analyzing the spatial relationships between a stove, a refrigerator, a table, and chairs, and aggregating all that context to form a high-level conceptual conclusion.
And how did the SE blocks handle that level of abstraction?
Flawlessly. They used an SE ResNet 152, and it achieved an 11.01% top 5 error. This comfortably beat the previous state-of-the-art model on that dataset, which was stuck at 11.48%.
Okay, so it can classify tiny images, giant images, single objects, and highly abstract scenes. What about object detection? Drawing precise bounding boxes around things.
They tested that on the COCO dataset, which is the gold standard for object detection and segmentation.
Okay, and how did it do?
They took a standard faster RCN and detection framework and simply replaced the standard ResNet backbone trunk with an SE ResNet. On the standard average precision metric, the SE ResNet 50 outperformed the baseline ResNet 50 by 2.4 percentage points.
Which is a 6.3% relative improvement.
that's exact.
Let's break down why channel recalibration helps with drawing a box. When a network has to draw a bounding box around a dog sitting on a couch, it needs to separate the pixels of the dog from the pixels of the couch.
It has to find the literal boundary.
Right, so by explicitly exciting the channels that track fur texture and globally suppressing the channels that track leather texture, the mathematical boundaries of the object become significantly sharper in the feature maps.
It makes the downstream job of the bounding box regression algorithm much easier.
That is exactly the mechanism at play. Better feature representations inevitably lead to better downstream localization.
And finally, they addressed the highly constrained world of mobile devices.
Because we know the SE block works on massive data center scale models. But what about phones?
They integrated SE blocks into MobileNet and ShuffleNet, which are architectures specifically designed from the ground up to minimize operations for older smartphones and edge hardware.
And did it help?
Even in these hyper-efficient architectures, where every single parameter is squeezed and spatial convolutions are stripped to their bare minimum, adding SE blocks consistently improved accuracy by a large margin for a trivial increase in compute.
Numbers, give me numbers.
On MobileNet, the top 1 error dropped from 28.4% to 25.3%. That is a massive 3.1% absolute improvement on a mobile model.
The numbers across the board are just undeniable. It is a clean sweep across classification, scene understanding, object detection, huge models, and tiny mobile models.
It really is a universal improvement.
But, numbers only tell you what happened. They don't tell you how the network is actually thinking. And that brings us to my favorite part of the paper. We are going to open the black box.
Yes, the interpretability section.
The authors didn't just take their ImageNet trophy and go home. They did something quite rare in deep learning literature. They actively tried to look inside the network's brain to see what the excitation operator was actually doing at different stages of the process.
It is a critical part of the scientific process. They started by proving that their core hypothesis that global information is strictly necessary for this to work was actually true.
So they didn't just assume the squeeze operation was doing all the heavy lifting.
No, they tested it with an ablation called the no-squeeze experiment.
How do you remove the squeeze without breaking the math?
They built a variant of the SE block where they removed the global average pooling operation completely.
Okay, so no more 1 by 1 by C descriptor.
Right. Instead of squeezing the spatial dimensions into a 1x1 vector, they replaced the two fully connected bottleneck layers with 1x1 point-wise spatial convolutions that maintained the exact same channel dimensions.
Meaning the parameter count and the computational complexity were exactly the same as a normal SE block.
Exactly the same. But the network no longer had a global embedding. The recalibration weights were generated strictly based on local output within the spatial map.
So it's essentially an SE block, but you forced it to wear the paper towel tube again. It can recalibrate, but only based on the tiny local patch it's currently looking at.
Exactly. And the result was definitive. Performance dropped significantly.
Let me guess, back to baseline.
Pretty close. The proper SE ResNet 50 had an error of 6.03%, while the no-squeeze variant had an error of 6.39%.
What is fascinating here is that this proves the extra parameters alone aren't what is providing the magical benefit. Adding more weights locally doesn't solve the problem.
The global information embedding averaging out the spatial data to get a high-level summary of the entire image is the vital secret sauce.
Okay, so we know it absolutely needs that global view to work. But what is it actually doing with that view? How is it turning those volume knobs?
To figure this out, the authors tracked the actual class activations across different depths of the network. They picked 4 very different classes from the ImageNet dataset.
What were they?
A goldfish, a pug, a plane, and a cliff.
Okay, very visually distinct.
Yes. And they looked at how the 50 different channels in the SE blocks were being cited when the network looked at pictures of these specific things.
So they basically hooked up an EEG to the neural network.
Essentially. And the visualizations they provide are illuminating. Let's walk through what they found layer by layer.
Let's do it.
In the early layers of the network, say stage 2 or the beginning of stage 3, the distribution of the excitation weights across the different classes is nearly identical.
Wait, really? Identical?
Yes. Whether the network is looking at a goldfish, a pug, or a plane, the SE blocks are turning the exact same knobs to the exact same volume.
Which honestly makes total sense if you understand how CNNs build representations from the ground up.
How so?
Well, in the early layers, a network doesn't know what a dog or a plane is yet. It is just looking for the most basic geometric building blocks. A pug has curved edges, a plane has straight edges, a cliff has rough texture.
It's finding the primitives.
Right. The network is essentially saying, at this stage, I just need to find all the edges and textures I can. Enhance all the edge detectors globally in a completely class-agnostic way.
Precisely. The early layers learn shared low-level representations. But as you move into the deeper layers, stages 4 and the early parts of stage 5, the activations become wild and highly class-specific.
The graphs start to diverge.
Radically. The distribution graph for a pug looks entirely different from the distribution graph for a cliff. The network is actively deciding that different high-level semantic features matter for different objects.
So it is dynamically cranking up the floppy ear and snout channels for the pug while totally suppressing them for the plane.
And simultaneously boosting the metal reflection and straight wing channels for the plane.
It is dynamically routing the information based on the conceptual context it has built up over the previous layers.
Yes. But then we reach the final layers, the very end of the network, right before it has to make its final prediction.
And something truly bizarre happens in the data.
At layers SE52 and SE53, the activations all push toward 1.0.
They saturate completely. Every single channel gets a weight of nearly 1.
This is a beautiful finding. Let's think about the math of the scale step. If the excitation weight for a channel is exactly 1.0, what happens when you multiply the spatial feature map by it?
Nothing. When you multiply by 1, the value doesn't change. The feature map just passes through completely unmodified. It's essentially an identity function.
Exactly.
By setting all the knobs to 1, the network is effectively turning the SE block off at the very end of the line.
The recalibration becomes an identity operator. And this perfectly explains that massive memory optimization we discussed earlier.
Oh, wow. Remember how deleting the SE blocks from the final stage saves 6% of the total parameter count with almost zero loss in accuracy?
This is the mathematical reason why. The network had already finished doing all of its complex routing and recalibration in the middle layers.
By the time it reached the final layers, the feature representations were already perfectly tuned for classification.
The network was basically saying, I'm good, the features are optimal, I don't need to adjust anything anymore. So you can just delete those blocks entirely and save the memory.
It is a stunning example of how taking the time to open the black box and actually understand the math can lead to direct, practical engineering optimizations. The SE blocks do all their heavy lifting in the middle of the network, supporting the increasingly class-specific needs of the model, and then gracefully step out of the way before the final classification layer.
Just so elegant.
It really is. It is a powerful reminder that architecture design isn't just about throwing more layers at a problem. It is about thoughtfully managing the flow of information.
Absolutely.
All right, we have covered the deep history of 2017 computer vision, the bottleneck math, the microscopic computational cost, the record-breaking results, and the black box activations. Now, it's time to transition to my favorite part of the show. It is time for our signature novel notion segment.
Excellent. I will provide our standard disclaimer for the audience. This segment explores outlandish, theoretical, but scientifically plausible ideas for entertainment purposes only. We are going to take the core mechanisms of the paper we just rigorously discussed and stretch them into unproven territory.
Please do not try to publish these as finished peer-reviewed paper.
No, definitely not.
Unless, of course, you actually build it in PyTorch and it works, in which case you definitely heard it here first.
Okay.
So for today's novel notion, I want to pick you an idea. Cross-modal squeeze and excitation gating, specifically for audio-visual recalibration.
Okay, I am intrigued. Walk me through the grounding mechanism. How are you adapting the standard SE block for a multimodal context?
So we know the standard SE block takes a spatial feature map, uses the squeeze operation to generate a 1x1x global descriptor, and then passes that through a bottleneck to gate its own visual channels.
It's a closed loop.
Right, a closed loop. But what if we break that loop? What if we have a multimodal model processing a video that has both sight and sound?
I see where you were going. You want to cross the streams.
Exactly. We have two separate neural networks running in parallel. One stream takes visual frames. The other stream takes audio spectrograms.
Two separate trunks.
We take the visual stream and we apply the squeeze operation to the visual spatial features to generate a global visual descriptor. But instead of piping that back into the visual stream to turn the visual knobs, we pipe that visual descriptor through an excitation bottleneck to gate the audio frequency channels.
No, wow.
And vice versa. We squeeze the audio spectrogram to generate a global audio descriptor and use it to excite or suppress the visual channels.
That is a fascinating scenario. Let's think through the theoretical implications of that cross-wiring.
Okay, let's map it out.
If your visual stream's squeeze operation detects the visual pattern of a dog's mouth opening and closing aggressively, that visual descriptor passes through the cross-modal excitation bottleneck and generates weights for the audio channels.
So it dynamically boosts the specific audio channels corresponding to high-frequency barking,
while simultaneously suppressing the audio channels that correspond to low-frequency background street noise because the visual context says, focus on the dog.
Yes, the visual context explicitly tells the audio network what to listen for, and the reverse is true.
How so?
If the audio stream suddenly hears a loud, sharp crack of an explosion, its squeeze descriptor gates the visual stream. It turns down the visual channels looking for calm, static textures like a blue sky, and highly excites the visual channels looking for rapid movement, bright flashes, and smoke.
So how would you design the first experiment to test this hypothesis?
Well, I would train a dual-stream ResNet on a massive data set of annotated video clips, something like DeepMind's Kinetics or Google's Audio Set. One stream processes visual frames, the other processes audio spectrograms.
Can you just wire them together?
I would cross-wire the SE blocks at every major stage. The squeeze from vision feeds the excitation of audio, and the squeeze from audio feeds the excitation of vision. Then I would compare its classification accuracy on complex actions against a baseline model that uses completely independent, non-crossed SE streams.
Let's do some probability mapping on the potential outcomes of that experiment. The obvious outcome, assuming the training dynamics are stable, is that it works extremely well for highly correlated audiovisual events.
Like things that naturally go together.
Right. Things like people talking, musical instruments being played, or glass breaking. The cross-gating would act as an incredibly efficient dynamic noise filter, using the clear signal from one modality to clean up the noisy signal in the other.
But the real magic is the non-obvious implication. Think about those bottleneck layers themselves.
The two fully connected layers in the middle of the excitation step.
Right. If you cross-wire them between modalities, those bottlenecks are forced to learn a shared latent space between vision and sound.
They have to mathematically translate visual concepts into audio routing instructions.
And here is the kicker. They were doing this without needing massive, complex, compute-heavy, cross-attention transformer heads. We know from earlier that the bottleneck math is practically free.
I see the application immediately. You could achieve sophisticated multimodal synchronization on highly constrained edge devices.
Like smart glasses.
Imagine augmented reality glasses. They have a tiny, low-power visual camera looking at the person you're facing. They use a cross-modal SE block to take that visual data, translate it through the bottleneck, and dynamically recalibrate the microphone channels to isolate that specific person's voice.
Suppressing the hum of the air conditioner or the chatter of the rest of the room.
It would be computationally microscopic compared to trying to run a full multimodal transformer architecture directly on a pair of lightweight glasses.
Exactly. It's taking the SE block's greatest strength, its extreme parameter efficiency, and applying it to the notoriously expensive problem of multimodal fusion.
It is a highly plausible theory and a great novel notion. It stays true to the mathematical spirit of the original paper.
Thank you. I think it could totally work. And that brings us to the end of our deep dive into Squeeze-and-Excitation Networks. If we reiterate the core lesson of this paper, it's a beautifully human one, really.
A philosophical takeaway.
Yeah. Sometimes when you are lost in the weeds, when you are staring too closely at the local details through a paper towel tube, the best thing you can possibly do is step back. You have to squeeze all that hyper-specific information down to get a global perspective.
Because it is only by looking at the whole picture that you can truly know which specific details you need to excite and which ones you need to ignore.
It is a lesson that echoes far beyond computer science. So as you go about your day, I leave you with this final thought to mull over. We've seen how elegantly and efficiently neural networks can learn to dynamically recalibrate their own attention based on global context. As our models become increasingly multimodal, taking in text, audio, video, and sensory data all at once, how long until these simple squeeze and excitation bottlenecks evolve into a global subconscious routing system for artificial general intelligence, silently and efficiently deciding which of its senses the machine should trust from millisecond to millisecond? Thanks for listening, and keep diving deep.